Hello. In this video, I'm going to show how to solve this train track problem where we have two line charges of charge density lambda each separated by a distance 2d, and we're interested in a point h above the center between them. Okay, so the first part of the problem asks us to use Coulomb's law to find the electric field at that point, the specified point. So by symmetry, the x and y components of the electric field cancel. This little chunk of charge over here is going to cancel the little chunk of charge over there in their x and y components. However, their z components are going to both be upward, so we're going to have a net z field upward the z direction. So we really don't have to find ex and ey. We only have to find ez. So let's find ez. So v is equal to, and I'm going to have to integrate over my chart. Well, sorry, not v. I'm going to have to integrate over my charge distribution. So I'm going to call this dE, where dE is the field due to this little charge here, dx. So that the little charge here, the charge dq is equal to lambda dx. So basically what I'm doing is I'm splitting the line charges up into a bunch of little segments that are dx long. I will find the field due to each one. In particular, I will find the z component of the field due to each of them. I will then add up, aka integrate up, all of those z components together to get the total field. So right now I'm going to find dE, meaning the field just due to this little component there. Okay, so dE is equal to q, or dq in this case, which is lambda dx over 4 pi epsilon naught r squared. But I don't want r. R isn't given in the problem. We are instead given this distance. We're instead given h and d. We're not given r. R is the distance between my little line, or little dx, and the point of interest. So how do I find dr? Well, we can use three-dimensional Pythagorean theorem. If you go in the z direction, then you go in the y direction, and then you go in the x direction. You can see there's the three parts there. You add them all together using three-dimensional Pythagorean theorem, and you get r is equal to the square root of h squared plus d squared plus, and then this distance here, I'm going to call x. So x squared. So if that's r, this is r squared, well, conveniently just kills the square root. So I end up with h squared plus d squared plus x squared. Awesome. So that's dE. In particular, dE will point in the same direction as the line going from our dq to our point of interest. So point off in that direction. Now I only want the z component of that. So if I do similar triangles, if I note I have this triangle here and this triangle, oops, try that again, here, I only want the vertical part here. If this is dE, I only want dE in the z direction. I only want the vertical component of dE. How do I get the vertical component? Well, this triangle here is similar to this triangle here. In particular, dE, z, so the vertical component over dE, so the fraction in the vertical component, is equal to sine theta, where this thing right here is theta. This is also theta by like trigonometry rules. Similarly, by this theta, the sine of that theta is also equal to h over r. So h over r is also equal to sine theta. Cancel, basically setting the two sines theta together, we get this is equal to that. We get dEz over dE is equal to h over r. Since we want to know the z component, we get dEz is equal to, well, dE, which is this whole thing here. So let me put that in. Lambda dx over 4 pi epsilon naught. And then this whole thing in parentheses, h squared plus d squared plus x squared times h over r. But r is this whole thing here in the square root, so I can just, that's basically a square root of this whole thing in parentheses, so I can just write this as 3 halves. I had 2 halves, aka once from here, and then another half from the r, so it ends up being like that. So that's dEz. If I want the full the full z component, I have to add up all the little chunks on both lines. So I'm just going to multiply by 2 times 2, so I can get my 2 lines, because they're both the same. They'll have the same contribution to the vertical component, so I can just multiply by 2 by symmetry. I then integrate from minus infinity to infinity to get add up all the little chunks along the line, so that I get the full full e component. So the e component, Ez, is basically equal to this integral right here. I'm going to simplify this integral just a minute here. So simplifying that integral, I can pull out the constants, and I get, so I pull out the constants, I get lambda, so let's zoom up on this here so I have better handwriting. Lambda h over 2 pi epsilon naught. It's 2, not 4, because of that 2 over here canceled with one of the 2's and the 4. Integral from minus infinity to infinity of 1 over h squared plus d squared plus x squared to the 3 halves dx. This is a pretty hard integral. I don't want to do it right now. I'm just going to look up the answer. In fact, I've already looked up the answer. So I'm just going to write down the answer. The answer is Ez is equal to lambda h over 2 pi epsilon naught, the same thing, and then I'm going to have my limit, so I'm going to write this in brackets. X over h squared plus d squared times the square root of h squared plus d squared plus x squared, evaluated at the limits x equals minus infinity and x equals infinity. Okie dokie. So how do I do these sticking infinity into this expression? Basically, I get infinity over infinity. But it's not so bad, because if I stick infinity in the top, x goes to infinity, and I stick infinity in here, well, infinity squared is infinity. And it's much bigger than h and d, so these h and d here are irrelevant. So then I get the square root of x squared, or square root of infinity squared. The square root cancels the square, and I just basically get x over x. The two x's cancel, so as x gets really large, this x in the numerator cancels this whole square root at the bottom, and you're left with just 1 over h squared plus d squared. Same thing happens when you stick in negative infinity, other than you get an extra negative sign at the top. So I can rewrite this as Ez is equal to lambda h over 2 pi epsilon naught. To write that quickly, it's getting boring. Okay. 1, because the x canceled out, h h squared plus d squared minus 1 in the top because we had a minus infinity this time, h squared plus d squared. Well, wouldn't you know, those are basically the same thing. They add together, just give us a 2, cancel that 2 there. We get EZ is equal to lambda h over pi. Try to write this a little better. Pi epsilon naught 1 over h squared plus d squared. So that is the electric field in the z direction. Let's take a moment to think about this. Does this make sense? Okay, first thing, what happens if d, or well, sorry, that's a plus, not a minus. Wouldn't have made sense. Okay, plus. So what happens if d is really big? So if d gets really big, then as d gets really big, this whole thing goes to 0, which basically means the two line charges are far away, you don't get any field. Sort of makes sense. What happens if h goes to much larger than d? Well, if h is much larger than d, or similarly, if d equals 0, the 0 goes away here. The h in the numerator cancels one of the h's in the denominator, and we're left with lambda over pi epsilon naught h. You may remember that the field due to a single line charge is pi over 2 epsilon naught h. Well, why do we not have the 2? It's because there are two line charges. You bring them together, basically they're a doubly charged line charge. So this does reduce to the answer you would get for a doubly charged line charge if d goes to 0. So this sort of has the right behavior. Okay, so that's part number 1. So part number 2. Let's do part number 2. Okay, so for question number 2, we are told to plot E as a function of H. That is what we want to just plot the answer we just got. Okay, so to plot this function here, there's two ways we can do this. We can just plot the mathematical function EZ as a function of H, or we can think about it. So if we remember our situation here, we have these two line charges, and we're wondering about a point H above them. So we can qualitatively ask ourselves, so what should the electric field look like? If we're right in the point between the two charges, the electric field should be 0 because the two line charges are canceling each other out. As we go up, we get a strong upward field, but then as we go further and further away, we're further away from the line charges, so the field falls off because the influence of the line charges dissipates as you're further from them. This results in an electric field which looks something like this. It's 0 at the beginning and then falls off. Or 0 at the beginning, goes up to a maximum, and then falls off, like so. And that is indeed what this function here will do as you increase H. Okay, so that's question number 2. Question number 3 asks us to perform a path integral to find V. So basically what we're going to do is we're going to perform a path integral from here up in order to infinity, because we know the potential at infinity is 0. So if we do a path integral from here to infinity, we can determine the potential difference, the voltage difference between infinity and here, aka what is the potential here. Okay, so let's do it that way. 3, we're going to use the fact that delta V is equal to minus integral from x initial to x final of E dot ds. In particular, for us, we are going to do V at infinity minus V at h is equal to minus the integral from h to infinity of ez as a function of h dh, because s is just increasing s is just the same as increasing h, because we're doing the path where we just we do the path from here up. So s is basically just h increasing. And the limits are going to go to h and infinity. Okay, so we call this thing here 0. The voltage at infinity is defined to be 0. We can then cancel our negative signs. And now basically we're going to just plug in our E that we found earlier in here. So if I do that, I get V of H is equal to, and you can look back up at what E is. It's this ratio right there. I plug this thing in right here, and I get integral for H to infinity of lambda H over pi epsilon naught H squared plus D squared DH. You can look up this integral. If you look up this integral, you find that the answer is V of H. You can pull out the lambda over pi epsilon naught, and then the stuff inside is equal to 1/2 ln of d squared minus or plus h squared. Don't believe me, take the derivative and verify this. H to infinity. Okay, now I'm going to stick in my two limits, and I get v of h is equal to lambda over pi epsilon naught. Okay, so if I stick in infinity, I get 1/2 the natural log of infinity squared. Who cares about the d if it's added to infinity squared? So basically we get natural log of infinity minus, and I'm going to take the 1/2 into the natural log. It becomes a square root. We get ln of the square root of d squared plus h squared. All right. That's pretty cool. So that's what that looks like. This is infinity. Natural log of infinity is infinity. So the voltage is infinity. May seem kind of strange, but it's really not all that strange. You've got a couple of infinite line charges. Maybe with an infinite line charge, you end up with an infinite voltage, as it turns out. The voltage still has a shape. It still has you can still say how it changes with position. This function here says how it changes with position, but it's basically got an infinite offset on it. Okay, so that's our voltage. We basically can just say equals infinity. Okay, so now that we have the voltage, let's plot it. So number 4 is to sketch a plot of that. So we can't really plot infinity, but we can say, well, less than infinite offset, you can plot voltage, relative voltage as a function of position. And that looks something like, if you plot this function, it comes out flat, and then it dies, and it kind of goes like that. It continues off down like that. So this is V as a function of H in that direction. So that's that. Notice that this line will just continue on down forever, which is why any voltage on here is an infinite value, because it's infinitely far above this, wherever this goes, which is infinitely far down. So it still has a shape, it's just infinitely offset. Okay, so that's the voltage. You'll notice flat here at the top. That's because there's very little field. Well, in fact, if you're right between the two line charges, there's no field at all. So there's no field here, meaning the derivative here is 0. Then the derivative gets steep as you get a high field as you start going up here, and then as you go further away, the field dies off again. It gets shallower, but the field never goes to 0, so the slope here never goes to 0 and it continues down forever. Okay, so that's how we plot voltage. The one last thing it asks us to do in this problem is to verify this voltage by integrating directly. So to find this voltage up here in part 3, we first took our electric field from part 2 and then did a path integral on it. There's an easier way to find voltage. You can find it without even going through the whole electric field route. You can just straight up add up the potential due to each of the little chunks of line charge along each of the 2 line charges, add up all that potential, and you would get the potential here. So let's do that now. In particular, so we're going to do, we're going to add up the potential due to a bunch of little dx segments. They are a distance r away from the point of interest, and voltage is basically integral over your charge distribution of dq, which is lambda dx over 4 pi epsilon naught, and then we need r. R is the square root of h squared plus d squared plus x squared, just like it was above. Okay, we want to integrate this over from minus infinity to infinity for the infinite line charges, and we're also going to multiply by 2 because there are 2 line charges. And then if you want to be extra tricky, you can note that the negative half of the line has the same effect as the positive half of the line. So you could really change this to 0 to infinity and make that, instead of a 2, a 4. And then it conveniently cancels that 4. And we get V is equal to lambda over pi epsilon naught. And then we can do this integral. So we do that integral. I'm not going to do it right here. I'm just going to look up the answer. If you look up the answer, it's natural log of x plus the square root of d squared plus h squared plus x squared, evaluated at 0 and infinity. If I stick those in, if I stick it in infinity, basically I get V is equal to lambda over pi epsilon naught, natural log of infinity plus infinity. Okay, that's just infinity. Natural log of infinity minus natural log. When I stick x in as 0, this is 0 here, this is 0 there, I get square root of d squared plus h squared, which, if you check, is identical to the answer we found up above. So that is the other way to calculate the potential. Okay, it also gives you infinity, technically. Okay, so that is how you solve this problem. Good luck with the rest of the homework.